All right. Wow. Whew. Okay. Before we get started, I'm super excited. Okay. Wave. Hi. Okay. Great. I have never been to Russia before. This has been an exciting week. Um, I would like to thank everyone for being here. Thanks for having me. Thanks especially to Yandex for sponsoring my trip and putting me up. It's been really terrific. Everyone has been just really, really nice. And I've been just really blown away by the hospitality and by everyone's English, which is way better than my Russian. But I really didn't know how good everybody's English would be. So I made a presentation that was almost all C++ because I figured we all speak that. I hope you appreciate the fact that this talk is going to be just all code, like start to finish. So if your English isn't that great, that's okay. You can follow along in our chosen language. Yeah. Okay. So I am a little bit about me. Been active in the open source community for about 13 years. Member of Boost. I got 4 libraries in Boost. I'm a member of the Boost steering committee. I'm a Boost release manager. I've been on the C++ standardization committee for about 12 years. And my full-time job at the moment is to bring the standard library into the modern age. So that's what I'm going to be talking about today. I'm going to be talking about my pet project, which has now become my full-time job, which is rejuvenating the standard library by adding range support to the standard library. I should say that feel free to stop me at any time and ask me questions. Happy to answer questions. I don't want to be leaving people behind. There's a lot of new concepts and a lot of strange-looking code. The solution that I'm going to be working through in this talk is probably not going to be looking like a lot of code that you guys deal with on a day-to-day basis. So if you got questions, fire away. Okay. So welcome to the talk. I'm going to be talking about ranges. I'm going to be talking about what they're good for. I'm going to be talking about what all the pieces are that make up the whole of ranges, how they all work together. I'm going to talk a little bit about why you should care about what ranges are, in particular, because it's a completely different programming model. Lets you program in a way that is very expressive, very concise, purely functional, correct by construction, all those good things. I'm going to talk a little bit at the end about standardization and where we are in the process, what's been proposed and what's going to be proposed, and when you might expect to see this stuff showing up in your standard library. I say that I completely stole the idea for this talk from, does anybody know D, the D programming language? Yeah, okay. There's a D wiki. Somebody did a really interesting post on the D wiki about ranges and using ranges to solve a particular problem. I thought this is a great problem. It's going to make a great talk. So I stole it and hacked it and implemented it in C++, and I think it's way better. So here's the goal. I'm going to write a command line program that you can format to the command line, the calendar for any year that you type in. Okay, so calendar 2015 prints it all out to the console. What's pretty interesting about this problem is dates and times are these really awful human systems that are nasty and inconsistent. Months have different number of days, and weeks start on different days each month. Some months are longer than others. Formatting is going to be really weird. There's this sort of impedance mismatch because we're going to be generating dates, obviously, in the order in which the dates appear in the calendar, but that's not the order that things get written out to the console. Right? Console is this serial thing, so somehow we're going to have to rearrange data on the fly, format it correctly, and print it all out. Seems like it's going to be, it's going to be really buggy, right? You can imagine if you sat down to write this, with a bunch of nested for loops, calculating offsets and manipulating strings. the chances are good your code's going to be a horrible mess. It's going to be ugly and long, and you're going to be finding bugs in it until the cows come home. But we're going to do it a little differently, and we're going to do it in a way that we guarantee is correct. Here's the solution. Yeah. Can everybody see that all right? We're going to be working through this one line at a time. And you're just going to see how all of the different pieces fit together. And in the process, we're going to learn all the different parts of the ranges library and how they all work together to make solutions. Okay. Step number 1 is pretty simple. Just create a range of dates. For this, I'm going to use the datetime library from Boost. Has anybody used the Boost datetime library? Okay, some people. Yeah, it's pretty handy. I don't want to have to do all the nasty date manipulation myself. It's fortunate that there's a library that does it for me. So this is terrific. I can create a date, November 5th, 1955. I can print it out to the console. And there it is. All right, 1955, November 5th. Okay, easy enough. Now I can create a range. Ranges in this talk are going to be taken from my library, which is a Range v3 library. You can find it on GitHub. That's the link right there. So this particular range called view iota, and it's going to print out it's going to be a range of all of the integers between 1 and 11. Okay. And what a view is, I'll say a little bit about what a view is. We all know what a container is, like a vector. A view is kind of like a container, except for the fact that the view does not own its elements. Okay. So views either reference elements stored elsewhere, or they compute elements on demand. In this case, this range computes elements on demand. Actually, it just spits them out one after another. And so when I execute this code, it's just going to print all the integers between 1 and 11. So the library comes with some IOStream inserters and extractors for making sure that you can just dump a range out to the console. It formats it in some default way for us, and that's what we get. Okay? Simple enough. Any questions about that? No. Okay. Yes? Where's what? Where's the 11? So it's a half-open range, just like iterator pairs. You've got a begin and an end, and the element that the end iterator points to is not included in the range. Kind of like, the way you deal with any standard algorithm. Just like when you have a container and you call begin and end, right? It's like, that's how those iterators work. So it's a half-open range, just like iterators. Yeah. Good question, thanks. So like I was saying, range views to any object that has two member functions, begin and end, just like a container. And begin returns an iterator. End returns, it could return an iterator. It could also return something that is merely comparable to an iterator. I call that a sentinel. So iterator-sentinel pairs, kind of a generalization of the model that's currently in the STL. You can kind of think of these as algorithms that get turned inside out, An algorithm, as you are already familiar with it from the STL, is you pass two iterators in and the algorithm eagerly does all of the work between those two elements. But when you turn that inside out, what you get is something that gives you two iterators and lets you walk through the range, and behind the scenes, the algorithm is executing as you step through it. So it's lazy and it's on demand. These things don't own their elements, so you can pass them around. You don't have to worry about expensive copies. And they're composable. I'll say what I mean about that in a little later. It's going to be one of the most powerful parts of ranges and views is that they can compose with sorts of actions in a powerful way. And they're non-mutating. So as you iterate through a data sequence, you're pretty sure that you at no point is any of underlying data getting mutated, so you can do things in a purely functional way, and you don't have to worry about threading issues or anything like that. Okay, so we've got dates. We've got this really handy view iota thing, which generates sequence of elements from start to a finish. So we should be able to combine the two of them to create a range of dates. So if I use view iota and two dates, beginning date and an end date, you'd like to think that this would be a range of dates. Unfortunately, it doesn't compile. And we get this message here, assert message, this weakly incrementable, and it says, the object passed to view iota must model the weakly incrementable concept. That is, it must have pre and post increment operators, and it must have a difference type. Okay. So one of the exciting developments in C++ is that we're getting a new feature added to the language called concepts. Concepts will let us check at compile time different properties of types. You know, if you guys have used the STL, chances are you've experienced horrible error messages when you've done something wrong, right? Yes. Yeah. Concepts aim to address that problem by giving us a way of saying in code what the requirements are on the types that you pass to generic algorithms. You know, this is a concept check. View iota only works with things that I can increment. Okay? If you can't increment something, I can't count from start to finish. Okay? As it turns out, dates from the boost datetime library are not incrementable. I don't actually know why. I've talked to the author of the boost datetime library, and he's like, I know, I'm sorry. Anyway, it was just kind of a snafu. So he's going to add increment operators to the boost datetime library. But in the meantime, we'll have to hack it. And I should say that, obviously, the range library that I'm using here, you don't need a compiler that has concept support. I've kind of implemented it in a hacky sort of way to emulate concepts, but you do get some pretty nice error messages. Oh, this is pretty good. Yeah, it's not bad. Okay, so this is the hack. I just kind of like open up the boost namespace, define the operators that I think really should be there, and then close the boost namespace, and I can kind of assert that after doing that, okay, dates are actually incrementable now. They satisfy this concept. Needless to say, I mean, it's not very polite to go opening other people's namespaces and jamming your own stuff in there. So in practice, this is probably not the right way to do it. But anyway, it works. And when you do that, right, I can say view iota. Sorry, I skipped over that part. View iota, and I can iterate over all of the elements, or the first 10 elements at least, because I want to talk about that in a second. Okay, take the first 10 elements from this range, from and to, and print out all of the dates. A couple of interesting things going here. One is this pipe operator. When I mentioned earlier that ranges and views compose, this is what I'm talking about. That this creates a view, right, a range of dates from and to, and this is an operation that can input a range and output a range by adapting it in an interesting way. And the pipe operation is how we compose these operations on views. If you've used the Unix command line, you've probably piped the result of one executable into another executable. And you can chain operations on the Unix command line using pipes. This is exactly the same thing, except we're chaining range operations. So, as you might think, this prints out the first 10 dates of the year. It's a lot going on there. Any questions about this code? Okay. Have I lost everyone already? Yeah.
Do you use for expression view iota from 2 pipe view take 10 expression templates, or your library boost broader?
Ah, okay. So am I using expression templates? No, this does not use expression templates at all. This is just an operator that takes in a range and spits out a range. It doesn't create an expression tree that then gets turned into a range later. It eagerly creates a new range.
Okay, thank you.
Yeah. Yeah, question?
Question about range 4 construct.
Oh, right.
Can't you use range 4?
Sure, that's a good question. Why use this stupid macro when C++11 has this really convenient range-based for loop? I had mentioned that sometimes ranges have iterators sentinels. So begin returns an iterator, end returns a sentinel. Sentinel can actually have a different type than the iterator. As long as these two things can be compared for equality and inequality, that meets my definition of a range. But it doesn't satisfy C++11's range-based for loop, which really expects begin and end to have exactly the same type. So if the types differ between what begin returns and what end returns, range 4, the built-in range 4, throws up its hands and kind of pukes. This macro is a temporary hack until we can change the language to support begin and end having different types. And there's actually support on the committee for making that change. So in the future, you won't need to do this. Yeah, it's just a temporary thing. Okay, great. So you could print out the first 10 dates of the year. But don't go reaching into people's namespaces and hacking their code for them. Yeah. Okay. So our next step, now that we've got a range of dates, is we start manipulating our range of dates in ways that are interesting to us. And what you find is that when you're dealing with ranges, the interesting programming model is creating structure within a range and then breaking the structure down in interesting ways. The first thing we're going to do is we're going to create structure. We're going to turn a range of dates into a range of ranges of dates by grouping the dates that are in the same month. And we can do that pretty simply with this guy right here, view group by, okay? What we do is we say all the dates in the year, and what the dates of the year is view iota, and here's like all the dates start January 1st, stop January 1st of the next year. That's all the dates in the year, okay? And then group them by this predicate, right? Takes two dates and returns true if they're in the same month and false otherwise. So what that does is, like, for every adjacent date in your range, group together all the ones that are in the same month and turn that into a sub-range. And what you end up with is a range of ranges of dates where each inner range is a month. Okay. So I can iterate over the months where this is going to be now a range of dates, and I could print out the first day of the month. And when I do that, I get the first days of the months in the year. Now, view group by is a really handy and incredibly powerful adapter. We're going to see it used again. But it's just one of many views that come built in with range v3. So it's one of the things that you might be able to see in a future version of the C++ standard. Now, just for readability, let's refactor this a little bit. This is the exact same view group by the same predicate that we had on the previous slide. All we did was we moved it out of here and into its own function. Let's call it by month. Okay. And we use C++ 14's automatic return type deduction. So I don't have to say what type it returns, which is good because this actually returns kind of a complicated type. So just say, compiler, why don't you figure out what the return type is? Okay. I just want to give this thing a name and call it by month so that I can do this with it. For each month in a year that has been carved up by months, do this thing. It's the same code as was on the last slide, it's just refactored for readability. Okay. And that's a nice trick. We're going to use that trick again. So I mentioned that group by is just one of many view adapters that come with Range v3. Here's a bunch of the others. Lots of powerful things to choose from here. These things combine together in really interesting ways. So the stuff that you might expect, you know, concatenate two different ranges, intersperse a value in a range, you know, make the range unique, zip a couple of different ranges into one range, stuff like that. Okay, well the next step's pretty obvious. Once we've grouped into months, we want to group the months into weeks. Okay, we're going to do the exact same trick. Here we use view group by again. And we group together all of the dates that are in the same week. That is, they have the same week number. Oh yeah, question?
Yeah. I want to talk about group by. Should the range be sorted before?
So the question is, should the range be sorted before called the group by? It doesn't have to be sorted, no. What it does is it walks through a range beginning to end, and if there are adjacent elements for which the predicate returns true, those get grouped together. It doesn't scan the entire sequence to find things that need to be grouped together. It only groups together adjacent elements. No. Question?
Eric, I have a little silly question.
Yeah.
Why iota is called as it is? Well, previously Bartosz Milewski couldn't answer this question.
Why is iota called as, so there, you know, I picked iota because there's already a standard algorithm that does this called iota in numerics header. And why does the standard library have a function called iota? And I think it's from, I want to say Ada or some other programming language. And it's just like, it's some like crazy Greek function that comes from some other programming language where it means exactly what the committee members wanted it to mean. So they just stole the name.
Okay, it's just a placeholder, as I see.
Yeah, it's just a placeholder.
Okay.
Yeah, I know.
Thank you.
Yeah, no problem. Okay, so grouping months into weeks, it's the exact same thing as what we were expecting. The only snag is that we've already grouped a year into months. So we're dealing with a range of dates. What we're going to end up with after we group the months into weeks is a range of ranges of dates. Things are getting complicated now. Okay. And in order to effect that transformation, we have to first iterate over all of the months and then carve all of those months up into weeks. So we use view transform. View transform visits every element in a range and applies a transformation function. Yeah.
Another question here regarding by week function and C++ 14, because I remember in C++ 11 you couldn't really take decal type of an expression that contains lambda.
Mm-hmm.
And what is effectively happening here is that we can just skip the decal type, return type in by weeks function. So I'm wondering, how does it really work?
Magic.
Because in C++ 11 you cannot do that.
I know. Honestly, I'm not a core language guy. I don't know why this is okay and the other thing isn't. That's a mystery to me too. I wish I had an answer for you. I don't know. Yeah. All I know is this actually works. Yeah. And it's cool. Yeah. I've always wanted to be able to decal type a lambda. This kind of gives me an easy out. Yeah. It's one of those things like, it's kind of like the Heisenberg uncertainty thing. If you don't ask the question, then it's okay. Yeah. Yeah. Okay, so here we transform every month by carving it up into weeks. That's this guy over here. Transform each month by carving it up into weeks. And now I can iterate over every month, right? Dates in year by month, and carve the months into weeks. So we get a range of ranges of dates. I know it hurts your head, but now we can iterate over the months, and then for each month we can visit each week, and each week is going to be a range of dates. I can transform each week by showing only the days, so like slicing off the year and the month, which I want to show that, okay? And print it out. And here's what we get. Well, it's starting to look like a calendar already, isn't it? A little bit. You can kind of squint and see that. So little by little, we're kind of massaging this range of dates that we started with into something that's starting to look a little bit like a calendar. All right. Great. The only problem with this is that the weeks need to be formatted a little bit more nicely, as we got to get everything all lined up in columns and stuff. So clearly we need to do a little bit of string processing here, and I hate string processing. But there's libraries to help you with string processing. There's one in Boost called Boost Format. I'm going to be using that pretty heavily. And I had to teach myself Boost Format in order to do this. And so, I don't expect you guys to know Boost Format already. And it's going to take me a while to explain it. So I'm just going to kind of wave my hands and say, this magic format string does what I say it does. And take my word for it. Okay. So let's have a function that takes a date and returns a string. And it's just going to format that day in an element that's 3 characters wide. That's all it does. It's going to justify a day in a field that's 3 characters wide. And you do that by saying this magic format string, that is format pipe 3 pipe, it's a field that's 3 characters wide, and take out the day, ignore the month and ignore the year, just print the day into a field that's 3 characters wide. That's all that does. Oof, okay. Let's break this down. It's called format weeks. So I'm going to be transforming a week, which is a range of dates, okay? And so what I'm going to do with it, I'm going to take the week, I'm going to transform each day, turning it into a string that's 3 characters. Each day gets a string that's 3 characters, and then I'm going to join all the strings together. That's what this guy does, and I'm going to talk a little bit more about this guy a little later. But you can kind of think of it as just you take all these different strings, glom them all together again. All right, what you get is a week, formatted week. Okay? But if you remember from the beginning, not every formatted week started on a Sunday. So there's going to need to be, in some cases, some white space in the front. All right? So if your week only has 3 days in it, Thursday, Friday, Saturday, you need a bunch of white space in the front. Okay? And that's what this does. Figure out how much white space we need, right? Build one string that has that many white space characters in it, and then jam all that together, and that's our formatted week. Okay. Now I can walk over all the months, carve it up into weeks, format the weeks. whoops, okay. I'm going to talk about join in just a second. Okay. And if I format the weeks, we'll see in a couple of slides the result of this code, sorry. Detour, I'm going to talk a sec about action join. Join, well, you can kind of think, like imagine a lazy join that takes a couple of ranges, I could iterate over it. When I finished iterating over the first range, I jump to the next range, okay? That's not what this is. What this is do something eagerly, take a bunch of characters, join them all together into a new string, do it eagerly, and the result is actually a container that owns its elements. So it's a totally different thing than a lazy join. It's an eager join. So these are eager sequence algorithms. They can operate and return containers as opposed to the views, which can't. But they're composable like the views, and unlike the views, they could potentially mutate their underlying sequences. Okay. This is how they stack up with views. Views are lazy, range actions are eager. These are lightweight and non-owning. These are potentially heavyweight because they take return containers. But they're both composable. Okay. Here are some of the actions that come like built into the library. Some split, sort, slice. These are pretty useful operations, things that you might want to do to containers. And they all take and return containers. Okay, so given the code that we had on the previous slide, right, we can create a range of dates, carve it up by months, lay out each month, now print it out. So for each month, print out all the weeks in the month. And this is what we get. That looks a lot like a calendar now. Yeah. And just a, checkpoint. We've written no loops. Right. Have you guys seen a single if statement anywhere in this code? No if statements, no loops. Every function that we've seen so far, in fact, is nothing but a return statement. That's pretty cool. And now we've got something that does something quite sophisticated. Right? Our program is totally stateless. I'm not mutating any state anywhere in the program. When you mutate state, that's where bugs happen. If you don't mutate state, well, it's pretty hard to write a bug. It's pretty cool. Okay, now what's missing here? Obviously we need like month titles. And we're going to need to lay things out months side by side. So we've got a month title and we need to pad the weeks so all the months take the same amount of vertical space. Month title's not that hard. Boost datetime lets us do it. Has this month as long string member function, so I don't have to localize my month names. So all I'm doing is changing the layout months function that we had in the previous slide. So in addition to this, which is what we saw already, month by week, format each week, I'm going to take month title of the first day of the month. Okay. I could have picked any day of the month. They all have the same month title. Okay. Turn it into a view, a range of one element. View single takes an element and turns it into a range. And then concatenate that range by this other range. This is a range of strings representing formatted weeks. This guy is a range of one element contains the month title. Now concatenate those together, and that will put the name of the month at the top of the month. And when I do that, now I get January, February, March. Okay. Has anybody seen code? Like if you sat down and started working on this problem, this is probably not how you would do it, is it? Oh. Okay. Okay. So since we're going to be laying the months out side by side, It's going to make our jobs a lot easier if each month taked up the same amount of vertical space. Right? So I don't know if you noticed here, February takes up 5 lines. January takes up 6 lines. So that won't work so well if we try to lay these out next to each other. So we got to make it all the same. So formatted month takes as few as 4 and as many as 6 lines. So we want to pad the short months with empty lines. That's all we're going to do. Same code as we had before, except we're adding something here we have this view concat that we saw before. We're going to concatenate another range. This is like a range of blank lines. First thing we do is we count how many weeks we got, and then 6 minus the week count, that's how many blank lines we need. Repeat n takes an element, repeats it a certain number of times. That's all. When we do that, now we get some blank spaces here. Just make our job easier when we try to lay stuff out side by side. Questions about that? Okay. So far so good, right? We've got a year, it's a range of months. Month is a range of strings. Each month has exactly 7 lines in it. We're sure, we're guaranteed by the construction. By month and layout months reusable. They work even if the input range is infinite. Say instead of laying out 1 calendar year, we lay out every calendar year. We could just keep spewing out formatted months forever, right? Nothing about our solution says that we need to stop anywhere. And we're not doing any allocation, right? So we're not going to run out of memory. It just keeps going. All right, things are going to get interesting now. We have to figure out somehow of getting things from this format into that format. And this is where I had to do some really hard thinking. It's actually a little bit easier than it looks, because what we have is we have a range of strings. You can kind of think of a range of ranges as a matrix, right? A range of ranges, rows and columns. And we need to get the matrix from here over here. That's the transformation that we're looking for. Okay. Can anybody describe in words how to go from that picture to that picture? Got to really think about it. Yeah, question. Oh, yeah.
We should group them by 3.
Yeah, group them by 3. So we group them by 3, then we still have things going horizontally instead of the way it is over there. See, January, February, March, January, February, March.
I think we need to transpose the matrix somehow. So
Group by
turn
3.
The rows into columns.
Group by 3, transpose. That's exactly right. Yeah, it took me a lot longer to see that than you. Chunk the months into groups of 3s. For each group of 3 months, transpose the rows and columns. Okay, can everybody see that? How if we kind of rip off the top 3 and then transpose them, transpose the rows and columns, we end up like that. And then the transposed rows and columns, we kind of like glue them all together. Yeah. That's exactly the transform that we need to get from our layout that was just 1 month after another to the side-by-side layout. Okay. Join the chunks, join the strings of the inner ranges. That is, you'll have 3 strings representing the 3 formatted weeks on a line side by side. You join those, right? Print them, take the rest of the day off. Go to the bar. Okay. chunking. There wasn't, when I sat down to write this solution, my range library didn't have any way of chunking a range. Chunking is an example of like taking a range and turning it into a range of ranges. So it's like building structure, okay? So somehow we have to implement this range. So far, what we've been doing is taking existing pieces of the range library and assembling them to do interesting things. Now we have to like create something new. We have to create a new range adapter, chunk adapter. That's what I'm going to show next. So we're going to write a range adapter. And the library comes with a handy range adapter that lets us actually implement new range types. Okay. What we're going to do, we call it a chunk view, and it's parameterized on an input range. We take in a range, turn it into a range of ranges by chunking it into blocks of 3 or 4 or whatever. And it's going to store like the chunk size, which is n, right? And the range adapter itself is going to be storing the underlying range for us. The real action is going to be going on in this adapter class. That's how we specify how we are changing the behavior of the underlying range. And what we're going to be doing is, like, instead of returning elements, we're going to return groups of elements. So let's stick that over there. Here's the adapter, right? That's this guy. And this is mostly boilerplate, but what I want to show you in particular is current, right? This is like when you dereference an iterator, what should be returned, right? Since we're chunking a range into a range of ranges, the elements are now ranges. So when we fetch the current element is actually 3 elements in a range. Whoops. So here, whatever our current iterator is, make a range from this point to the very end of the range, and then take the first n elements of that. That's going to be 3. Okay. So our current, rather than returning an element, is returning 3 elements. That's what this line does. Right. And when we advance an iterator, we advance it 3 elements. This is how we implement chunk. Okay. Now, okay. We want to be able to take a range, pipe it. Right, we remember how we use the pipe operator to chain operations. So we need some chunking pipe operation. This is how we do it. We use something called makePipeable. And this is kind of weird, a little confusing. So I'm going to spend a little bit of time talking about makePipeable. This is how we build these adapter types. Chunk, logically, is an operation that takes 2 arguments. It takes a range, the range to chunk, and it takes the number of elements in each chunk, 2 arguments. But it's going to be in a kind of strange syntax, right? Here's the first argument, the range. Here's the second argument, the number of elements in each chunk. This is the syntax that we want. It's kind of like a function that takes 2 arguments, but with a really weird syntax. So how we do that, if you think about it, chunk of n must remember n and return an object that's got an overloaded pipe operator. And it does that with this makePipeable helper, which seems kind of like it would be a hard, complicated thing, but it's actually only a couple of lines of code. makePipeable takes a function of 1 argument. Okay? And it returns this pipeable thing that just remembers that function of 1 argument. And pipeable remembers that function and has this operator pipe that takes 1 argument and passes it to that function. It basically just rewrites a function call into A pipe B. That's what that does. Simple enough. So look again at how it's actually used. Here we've got chunk. You pass it the chunk size. And to make pipeable, we're going to pass a function of one argument. It's the range. Okay. But it's a lambda that captures the chunk size. So if you've done functional programming, anybody done functional programming? Oh, a lot of people. So you guys know what partial evaluation and currying are? Yeah. You have a function that takes two arguments. You call it with one argument. What you get back is a function of one argument. And that's what's going on here, right? We take this argument, we bind it in a lambda, right? So it remembers that argument. And now we get the second argument, which is this range. And now that we have both arguments that chunk needs, we can create a chunk view from it. So chunk view, and we say, pass it all of the elements from this range. And we return a chunk view. Now I know that's really loopy and indirection-like, right? But stop, think about it for a while. It should make sense. Yeah. And it's used like that. Vector of integers. Chunk the vector of integers into groups of 3. And you could print them out. There's the first chunk, there's the second chunk, there's the third chunk. And this last chunk doesn't have 3 elements in it. That's okay. Just get as many as you can fit in there. So any questions about like how to create a range adapter? Sorry, it's complicated, I know. There's a lot going on. Yeah.
What does mean a friend?
The friend function?
No. Friend on the previous page.
Oh, yeah. This guy?
Yeah, yes.
That guy?
Usually friend declare some function which will be defined out of struct or class. And here.
Yeah. So this is a friend function. I could have defined it as a just a regular free function, but I don't know. This is just another way of doing it. What was that? Yeah. So it does interact with name lookup. So the friend functions get automatically generated, but really making it a free function probably would have been less confusing and also would have been found just fine. So it doesn't need to be a friend function to answer your question. Yeah. If, on the other hand, I had made this a private data member, which I should have done if I were being cleaner, right? So if this were private, then making it a friend would give it access here to that private member. Looked like maybe you didn't get that quite so much. Okay, so it's for friends have access to your privates. No, I bet you didn't know that. Yeah. So if this were a private data member, and if this were, instead of being a friend, were just a free function declared, say, right there, right? Then that free function, right, would not be able to access this if it were a private data member. Because free functions don't have access to private data members of classes and structs. Friends, however, do. That's the only difference. Yeah.
have a class or struct instead of class here. So the fun actually is a public member, yes?
Right, right. So this is a public member, which is, well, the point was it doesn't need to be a friend. Yes, it's true. It doesn't need to be a friend. If this had been private, which it isn't, then it does need to be a friend. Yeah. All right. Okay. Okay. So there. That's how we write a range adapter. So it's kind of interesting. It's good to know that if the range library doesn't have the adapter that you need to get your job done, you could always just write your own. Okay. Now, transposing a range of ranges. Remember we had said that our first step is to chunk into groups of 3. Okay, we got the chunk adapter, that's great. Now we need to transpose ranges. I had no idea how to do this. I really didn't. I tried a whole bunch, nothing was working. So I had to sit with the problem for a couple of days. And well, the problem really is that these things, when I'm transposing data that's being generated on the fly, and you need to do it in a lazy sort of way. Certainly, like if I have a range of ranges, that is basically a matrix. If I had that matrix saved in memory somewhere, okay, if it weren't being generated on the fly, if it were like, vector of vectors, right, then I could certainly transpose stuff easily enough, right, because I can like mutate stuff in place and jam values from here into here and vice versa, right, so transposing would be a piece of cake. But that's not the situation here. We have data that's being generated on the fly. It comes at us in a certain format. We want to present it in a different way, in a different order. And we need to do that transformation also on the fly. So I had no idea really how to do that. Then I had an aha. Okay. So what we have right now, we've got a matrix, a range of ranges, strings. Okay. And we have it laid out like this. Now, what we can do, right, we've got this structure. We can destroy the structure by doing a certain kind of traversal. We can interleave all the elements and get back something that's flat. We turn a range of ranges of strings into just a range of strings by iterating in this order. Okay? Does everybody see that so far? Yeah. And now we chunk. And we group these guys. Right? And we get this. We group these guys. And we get that. And now we've just transposed a range of ranges that are generated on the fly. Everybody see how I did that? We interleave like this. Okay. And then we chunk. And that's transpose. Transpose is an interleave followed by a chunk. Okay. Well, that's great. We already have chunk. It's already written. We don't have to worry about that part. We just have to worry about interleave now. Okay. So here's how we create a new interleave adapter. Logically, what it works, the way it works is we've got about 3 ranges. We want to store 3 iterators. And we're going to march all 3 iterators down like that in lockstep and visit each element and then advance, and then visit each element and then advance, visit each element. So that's how we're going to do the interleave. We've got a vector of ranges. And we're going to be using range facade. This is another helper. Rather than adapting an underlying range, we're going to be creating a range from scratch. Okay. And we're going to implement a cursor. You can kind of think of a cursor as an iterator, but without the complicated iterator interface. When you're implementing a cursor, rather than implementing operator plus plus and operator minus minus and all that other stuff, you just implement current and next. And that's an iterator. Okay, so let's look at the cursor. I said we have a vector of iterators, right? This is the vector of iterators. The current element, where am I in marching across, right, my iteration? What range am I iterating in, right? And then when I say next, okay, I'm going to increment n, check to see whether I've reached the end. Okay, that's going to go from 0 to 3, 0, 1, 2, and then when it reaches 3, it wraps, and then I bump all the iterators forward 1. This is how we do interleaving. Okay? And we're done when at least one of the iterators has reached the end of its range. Okay? Then we say, okay, well, I can't go any further. One of these ranges is expired, so I'm done. Okay. And here's make pipeable. Now we do interleave, just the same way we did chunk. This is a function of one argument. And now we can interleave elements. So say we have a range 0, 1, 2. I repeat it 3 times. So I have a range of ranges 0, 1, 2, 0, 1, 2, 0, 1, 2. And I interleave them. I get 0, 0, 0, 1, 1, 1, 2, 2, 2. I start with a range of ranges, and I interleave, destroying the structure that's there, flattening a range of ranges into a single range in a very particular way, interleaving the elements. So remember, we're storing 3 iterators. We'll store an iterator that points here, that points there, and that points there. And when I increment the iterators, first I print this one, then I print this one, then I print that one. Then I bump all the iterators forward 1, there, there, and there, and so on. Okay. And now that I have chunk and I have interleave, I have transpose. Transpose is just an interleave followed by a chunk. And now taking that same input range, I can transpose. And starting with 0, 1, 2, 0, 1, 2, 0, 1, 2, I go 0, 0, 0, 1, 1, 1, 2, 2, 2. I've transposed the rows and columns. Yeah, question?
Views are lazy and actions are eager.
That's right.
Shouldn't transpose be action, not view?
Should transpose be an action? So it could be an action. You could have a transpose action if you wanted. The input here, though, is data that's lazy and being generated on demand. And the advantage of having a lazy transpose is that you've preserved that. It's still lazy and it's still on demand. I can transpose a range of infinite ranges. Right? If I have a range of infinite ranges, it goes like this forever. I can transpose that, right? And I end up with an infinite range of ranges that goes down this way. Yeah? If you tried to do that eagerly, you know what would happen? Yeah. You'd blow your memory. Yeah. Question?
One more question here.
Sure.
So the views are lazy
Yes.
by design.
Yeah.
But when you allocate that vectors that you mentioned before, so you need to know the length of the interval you need to wrap into the chunk of iterators.
Mm-hmm.
As far as I see, so you need to stop somewhere. You cannot create an infinite vector of iterators.
Right.
So it already became eager there.
Yeah. Eager in one direction. Right. So the example that I gave, like a range of infinite ranges, that works. Transposing an infinite range of ranges doesn't work, given this implementation, because I would be trying to create a vector of an infinite vector of iterators, and you can't do that. So.
Okay, so the basic limitation is that you need to work on the limited ranges somehow.
Right, right. So if you're going to transpose, it is a limited solution. You can't transpose an infinite range of ranges. And I suppose you might be able to figure out something clever, maybe by doing some sort of like a Cantor diagonal
exactly.
visitation. I haven't really investigated it that deeply yet. You know, I was happy just to figure this out. Yeah.
Oh, okay. Thank you.
Okay. Yeah. Yeah.
But how about runtime speed in compare with traditional approach, if cycles and if statements?
Sure. So how does this perform? That's a good question. I didn't implement this in a traditional way to benchmark it against. Right? It would have been really kind of an awful solution. As I had mentioned at the beginning, like a bunch of for loops, bunch of offset manipulations. I didn't implement it, so I couldn't speak from experience on how this performs. I could say there is some overhead here. Like every interleave iterator is going to store a vector of iterators. Vectors of iterators are dynamically allocated, so copying those iterators is going to be kind of expensive. That's one thing. A lot of the computation that's being done here, though, is being done lazily without allocation. You're generating elements on demand rather than like allocating a range of ranges of strings and doing string manipulations that are going to be creating a lot of temporary strings and doing string concatenations. That stuff is not happening so much here. It's happening some, but not so much. When you're generating stuff on the fly, you don't have to pre-allocate a whole bunch of memory just to have scratch space to do your work. There's very little scratch space is needed by this solution. Yeah. In other cases, things can be done entirely lazily and without any allocation at all, and in a way that is very transparent to the compiler, can be inlined and optimized very well. Yeah.
Question is about debugging. Is it, you said that there is no cycles and no conditions, and these cycles and condition are source of errors, and it's very complicated work with ranges, and I think there is a lot of source of errors and how to find them in this code.
So how do you find the errors in the code? The first point is that by writing code this way, what I have found is that if your code compiles, it is going to do the right thing, right? It might not give you the result that you want, right? But you can tweak things until it does give you the result that you want. And then your code it handles error cases naturally, like border cases, off by ones. You're never really dealing with off by one errors. They just don't appear in solutions like this. If you are experiencing problems, like one problem that might typically come up in a solution like this would be a memory error, that is a range that is referring to data that has gone away. Those can actually be really difficult to find, and I'm sorry, I don't have a magic bullet here. Debugging these applications can be really tricky when you have a memory error. But those are the sorts of errors that you're likely to see. You're not likely to see a whole lot of logic errors, off by ones, that sort of thing. I found that debugging an application like this is much simpler because I can use the compiler to find my errors for me, whereas using for loops, calculating offsets by hand, it's all on me to find the bugs. Yeah.
May I ask a question? You said that if something here compiles, then it probably works right.
Yeah.
And this library is highly functional.
Yes.
May I do a conclusion that you have been inspired by some functional language, for example, Haskell?
For example, Haskell. Yeah. So maybe you recognized the interleave function from the Haskell prelude.
Yeah.
Yes. Well, it's exactly where I got it from. And there's a lot of functional programming that goes on behind the scenes, but the programming model is definitely different for C++ because, well, it's less different than you would think, but sometimes you really need to do things eagerly. And in Haskell, that's very hard. But in C++, it's very simple to do things eagerly. All right, you just iterate over it all at once and put it all in a container and pass it around, and you're done. Whereas in Haskell, you don't really have that option so much. So yes, it's inspired largely by functional programming, but in a way that we also have the power of imperative language and eager evaluation.
Okay, so I would like to point that there is simple solution of the transpose problem. It's the recursive function which takes the first element of your range, which contains ranges in the maps over the first elements of these ranges and takes for
yeah. So I tried to port the transpose from the Haskell prelude into ranges and found that I couldn't. The transpose function from Haskell's prelude works on lists and lists of lists. And it's really easy when the types of things don't change when you transpose them, but when the types do change, right? So the Haskell preludes function takes a list of lists and outputs a list of lists. And that makes it so much easier to write. This, unfortunately, you have a range of ranges where each internal range has the types of the internal range differ from the types of the external range. And so doing the transpose, you need to create something of a totally different type, and it makes the solution much more complicated. I was unable to port Haskell's transpose into C++ in a straightforward way.
Okay, thank you.
Yeah. Okay. So we're pretty much done. These are the only steps that remain, and I'm kind of going to skip them because we already know how to do all of that stuff. So here, we've got by month, layout months, chunk into groups of 3, transpose the months, join those transposed months together, and then join the strings on each line. And that's it. Just write it out to the output iterator. Transpose months is as you would think, right? Given a range of strings, transpose them. And then join months. For each month, join each string in each month. And when you do that, you get the calendar. That's the whole thing. Still, not a single loop anywhere in the program, and I think there was one if statement. Right? It's kind of cool. So let's look at this one more time, right? I'd say all of this stuff composes really well. We've seen a bunch of parts that compose really well with the pipe operator. Everything's pretty much reusable. This stuff works with infinite ranges. I can show n months side by side, right? Notice, if I change this to a 4, I get 4 months side by side, and that all just works. Or 5, or whatever. I can make that a command line parameter. I could have people tell me how many months to format side by side. Right? I just got all that for free. Not a single loop. The code is correct by construction. I'm pretty sure this bug handles all boundary cases, doesn't have a whole lot of bugs in it. I'm sure if I did it the other way, I'd be less confident to say that. So let's look again at the whole solution. What I coded in yellow here is stuff that has to do with the problem, specific to this problem, like formatting a calendar, manipulating dates and string manipulation, that sort of thing. What's in green is code that is perfectly general and totally reusable. Chunking, interleaving, transposing. None of that code has anything to do with this particular problem, can be reused in other projects. This is how I like to write code. I like to write code so that as much of the solution as possible is totally general and reusable, right? So I think we did a pretty good job here with the balance, about half and half. But I'm a library developer, and that's how I operate. Okay, so yeah, question.
It's an interesting way to think about problems, and thank you for the ideas. But question like that was asked before, but I'm going a little bit rephrase it. Did you look at what assembly code does this program produce? And it's interesting to think about what kind of what code does get optimized out completely, and what actually executes on a CPU.
Right. Okay, so that's actually a really good question. And for this solution, I did not look at the generated assembly, but for other solutions, I have. If you go on my blog, ericniebler.com, and you look for a blog post called range compositions. No, range. Well, I'll remember in a minute, right? What is the feature in another? Like Python has comprehensions, range comprehensions. Python has a feature called list comprehensions. Haskell has them too. It lets you generate data on the fly in a list in a very concise, kind of like almost like a SQL-like syntax, right? I realized that using a little bit of functional programming magic, I could do something similar with ranges and have range comprehensions, a very concise syntax for generating data on the fly, creating data generators. And the example that I work through in that blog post is generating the infinite list of Pythagorean triples. So things for which a squared plus b squared equals c squared. Just iterate through like all of them as fast as you can. And I programmed it in Haskell, and I programmed it in C++ using my range library. And the range library totally blew Haskell out of the water if you compile with GCC. If you compile with Clang, the Clang code was 17 times slower than the GCC code. And that's because the Clang optimizer works in a totally different way and missed a fundamental optimization, which caused an enormous swath of code to not get inlined when it should have. GCC had the right optimization and did the right thing. So that's kind of a roundabout way of saying your mileage may vary. And it really depends a lot on your compiler and how good your compiler writer team is. So I should say that like there's nothing about what you see here that should keep a compiler from optimizing the code to optimal assembly. And in GCC's case, on that particular example, it all optimized away. And it was like within 5% of like hand-coded C with raw loops and go-tos. So, yeah.
Thank you.
Okay, speaking about performance and the memory consumption, could you analyze the result logic in terms of a big O notation? How much does it consume memory? How much iterations or some kind of performance marker you have So as far as I see, ranges are completely functional, so they have no state. But I think there may be some problems analyzing the result algorithm.
So it's actually quite simple to analyze the complexity of ranges and views. Views in particular, because they iterate through as you iterate through the result range, if it is adapting an underlying range, it traverses that underlying range just once as you go through it. So these things compose, like, if you are, say the transform view, right? You take a vector, you apply a transformation to each element. Now, if I iterate through the resulting view, underlying, right, I iterate just once, you traverse each element just once. So it's all linear, right? That's my complexity. It's all ON, okay? Looking at this solution, the calendar application, I can have it spew out an infinitely formatted calendar, right? Just going to keep spewing and spewing and spewing. Memory usage for that program is going to be constant time. It doesn't grow, right? It allocates as much memory as it needs, and then it's just like a loop. It just keeps going. So order 1 memory usage.
Cool. Thank you.
In your talk, you said that week starts with Sundays. Here in Russia, we usually suppose that it starts with Mondays. So how can we tweak your program to support that format?
So that's actually a really easy change to make. And let me see, all the way back to where we were formatting the weeks. Let's see if I could go all the way. If I had it in front of me, I could just jump there. What we're looking for is by week. Where did that go? There. Okay. You notice this comment right here. ++A, because week number is Monday through Sunday, and we want the Sunday through Saturday. Well, I'm an American. I want Sunday through Saturday, right? But you are not an American, and you don't want Sunday through Saturday. So you would nuke this ++ and nuke that ++, and you would get the European calendar instead of the American calendar. Good question. Yeah.
I have a question about place when we process months with a short amount of days. Could you please several next slides?
Okay, what was the question? When you padded with extra space? Was that it?
Yes, this slide.
Yeah.
We see the variable we count and we call distance for months. I suppose that months range should be finite here. Yes, is it true for when we run this program for potentially infinite range?
Well, we can be certain that this is not an infinite range, right? Because this is a range of dates representing exactly 1 month. Months are finite, guaranteed. Yeah.
Okay.
Yeah.
Whole thing.
Phew. Yeah. Some months seem longer than others, though. Okay. Yeah, another question.
A single simple question is about debugging. Imagine we have a more complicated things that formatting a single day number, and instead we have some weird algorithm that crashes on every, say, 65535 value. How would I debug it conveniently if all counters I might specify for debugging session for watchdogs are behind the hood. They're in some macros like range iterators, etc.
Well, I don't really have a good answer for that. Certainly, when we the range library has its own adapters. Those are implemented using range facade, range facade, and range adapter. They have members that you can set breakpoints on, like the current member function, which dereferences, which gets called when you dereference an iterator. The next member function. So you would figure out what operation is causing the crash. Is it when I increment an iterator? Is it when I dereference the iterator? And then you could figure out like what member to set a breakpoint on and try to step through the code that way. I'm not going to lie to you, stepping through range code like this is an exercise in frustration. If you think about like the final solution, right? I have this input range and I pipe it through all of these adapters and I end up with like this mongoid complicated range at the end. I pull out an iterator. This is an iterator that is going to format the entire calendar, right? You can imagine how much code that gets executed when you dereference that iterator or when you increment that iterator, right? It's layers and layers and layers and layers. So debugging this is actually going to be quite hard if you actually need to. I think that you're going to spend less time debugging if you write code like this, though.
Yeah, the good case is, of course, you compile, and as soon as you compile, you get the result. In worst case, I'm afraid, well, view this sample crash DDD, for instance.
Mm-hmm. Oh, sorry, what was the question in there?
Have you tried to debug it? Say, view this, the code generated after handling all these templates crash some old-fashioned debugger like DDD?
In that case, what I have found works, and I haven't spent a lot of time doing this, is to break it up into parts and use printf debugging. Yeah. Yeah. Yeah.
To continue all of the previous questions, how to test this code?
How to test it?
Yeah, I don't know. You have a simple composition here, and if I will have more complexity composition in my work, I see the way to separate different presentation layer here, but I don't know how to test it.
So you have these different elements that you can compose, that compose orthogonally. Chunk view, interleave view, transpose, okay. You can test chunk in isolation. You can test transpose in isolation. You can test those two operations together. You can test the entire sequence, like you can do some black box testing on this thing end to end, right? When you have operation pipelines, right, you have these things that can be tested in isolation in addition to, right, end to end. So you can break the problem up that way, test individual pieces. I don't know, is that answering your question?
In this way, we should use our test data for every separated layers. Yes.
You can send your data in like end to end. You can create new test cases to test just individual pieces. That's how I've done it myself.
Okay, let it be. Thank you.
Yeah. Okay, so now I got to get all the way back to the end. Let's see, how do I apologize to make you guys sit through all of this. Okay. Okay. So ranges and standardization, you guys might wonder where we are in the process. The range concepts and the range algorithms have already been proposed and are currently working their way through the standardization committee. The view adapters, the actions, and the facade and the adopter helpers haven't been proposed yet. I haven't written the proposals just because I lack time, but they absolutely will be proposed. I'd like to see all of this in the standard. So here's where we are. In May, I presented a paper, the cursory review of the wording. What's going on right now is the detailed wording, having regular teleconferences with the committee members about going through the proposal, which is 120 pages long, going through it line by line, making sure that it says what I intended it to say. And then in October, hopefully, we'll get a TS, that's a technical specification. We'll vote initial wording in, and we're going to continue refining the wording, and at some point, while that's going on, I'll make other range proposals for infinite ranges, range views and actions, facades, adapters, that sort of thing. And at some point, the TS will be approved. That means we will ship ranges as a separate standard. Ultimately, what this is like a separate version of the standard library that's going to be in a different namespace. So you'll have all of the things that are currently in the standard library in a different namespace, maybe std2, whatever. And then at some point, that's all going to be merged into C++ proper. That's the idea. Okay, here's where you can go to find out more. Here's the actual papers that the committee is working on. Okay, and here's where you can get my Range v3 library where all of this stuff is implemented in C++ 11. Okay. Thank you guys a lot for listening. And if you guys have any more questions, I'm happy to take them.
Your ranges library look similar to LinkU in C#, and I think if I can write such program in C# without loops and if statements, and are there any advantages of LinkU, or it is kind of LinkU implementation in C++?
It's kind of a what implementation?
LinkU in C#.
Oh, Link, yeah. It is an awful lot like Link, and I don't claim to have invented these ideas. Certainly there was a lot stolen from Haskell. There's some ideas from Link, and I think that's a good thing. These ideas have been proven elsewhere, and I'm just not a C# guy, so I want it in C++. Yeah, I don't want to pay for the managed runtime environment. I want native code. I want it to compile down as tight as small as possible. I mean, we're all C++ programmers here, right? So, yeah. Cool. Any other questions? Right. I think we're finishing a little early. You guys get to hang out, and yeah, cool. Thanks a lot, guys.
Talk at 12:30, and the coffee break will start at noon, just across the hall. And sure, no questions. Just hit guys with Haskell in the head, so yeah, it will take a while, but I hope you will be here for next day, today and tomorrow, yeah. So I think any discussion, like not here but after, hopefully feel free to ask. Yeah?
Yeah, please. Ask me any questions you got.
Okay, thank you again for coming and for the great talk.